Section 8.1 is all about sequences. Sequences are typically given one of two ways. They're either explicitly defined or recursively defined. You're probably a little more familiar with an explicit formula. Explicit formula is a formula that gives the term's value based on the term number. So if we are looking for the 15th term, you would just plug 15 into the formula and it would spit out what the 15th term is. So an example would be a sub n. A is the term, n is the term number, is equal to 3 plus 2n. So if we needed the first term of this sequence, you would plug in 1. A sub 1 would be 5. Second term, a sub 2 would be 4 plus 3. A sub 3, you would plug in 3, 6 plus 3, and so on. A recursive formula that gives the term's value based on the previous term's value. So an example there, they would need to give you the first term. A sub 1 equals 4. A sub n is equal to, this should say, 3 times a sub n minus 1 plus 6. So in this case, my first term is 4. My second term would be 3 times a sub 2 minus 1. So a sub 1 plus 6, and a sub 1 we know. So a sub n minus 1 simply means the previous term. So you would plug in 4 here, giving us 12 plus 6, 18. A sub 3 would be 3 times the previous term, 3 times 18 plus 6, whatever that is, and so on. Explicit formulas are generally better, simply because if you needed the 100th term, you can get it very quickly by plugging in 100 and getting 203, whereas here, if you needed the 100th term, you would have to find all the terms before it. Recursive formulas sometimes are a little bit better, simply because it's easier to see what you're doing to each number. Like here, you're just you're taking the previous number times 3 plus 6. Here, it's not necessarily obvious that the pattern here is plus 2 plus 2. Example 1 asks us to write a formula for the sequence below. If we were to write a recursive formula, let's do it each way. A recursive formula, we would say the first term, a sub 1, is 88. And notice each term we're doing minus 3, minus 3, minus 3. So the nth term would be the previous term minus 3. Notice recursive formulas generally pretty easy to write. To get the explicit formula, a couple different ways you could do it. One way is you could recognize that this is an arithmetic sequence because we're adding or subtracting the same thing over and over again. And then maybe you remember the formula for an arithmetic sequence. We did it way back in August, September. So it would be a sub n is equal to a sub 1, 88, plus the common difference, which is negative 3 times n minus 1. That's what we have here, 85 minus 3n. It's a plus 3 here, no, minus 3. 91 minus 3n. If you don't remember the formula here, another way you could do it, we're subtracting 3 over and over again, so we know it's going to be minus 3n. And when I plug in 1, I want to get 88, which means I need to start with 91 and subtract the 3n. And then you can verify it by plugging in 1 to get 88, 2 to get 91 minus 6, 85, and so So that was examples 1 and 2. One's doing it explicitly, one's recursively. Example 3 here wants us to write the first 5 terms of the sequence. It gives us an explicitly defined formula. So a sub 1 would be 1 plus cosine of pi times 1 over 2. Cosine of pi over 2 is 0. A sub 2 is going to be 2 plus cosine of 2 pi over 2. Cosine of pi is -1. A sub 3 would be 3 plus cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. Whoops, 0 plus 3 is 3. 4 plus cosine of 4 pi over 2. 4 pi over 2, that's 2 pi. Cosine of 2 pi is 1. And so on. 5 plus cosine of 5 pi over 2. Cosine of 5 pi over 2 is 0. So 1, 1, 3, 5, 5. You do this one. You try this one. Pause the video. Try to find the first 5 terms. Once you think you have it, start the video right back up and verify. So here I have positive 1. 1 factorial is 1, so we get 2. Two factorial is 2, -1, and so on. So I've got the rest of my work here, 2, -1, 1/3, -1/12, 1 over 60. Notice the -1 to the n plus 1 is going to make it alternate back and forth between positive and negative. So would -1 to the n. If we have -1 to the n plus 1, notice the first term is going to be positive, whereas -1 to the n, the first term would be negative. So these are the two you primarily would use if we are alternating back and forth between positive and negative terms. -1 to the n will start us with a negative value. -1 to the n plus 1 will start us with a positive value. Example 4 asks us to write an expression for a sub n. 18, 15, 12, 9. It doesn't state it here. Let's write an explicit formula is what we're trying to do. So a sub n -3, -3, -3. So we are subtracting 3 over and over again. My first term needs to be 18, so I want 18. I want something -3. When I plug in 1, I get 3 here. To give me 18, that should be 21. And you can verify. Plug in 1 gives you 18, plug in 2 gives you 15, plug in 3 gives you 12, and so on. Notice this one, 5, 10, 20, 40. This time we're multiplying over and over again. Times 2, times 2, times 2. So we've got 2 to the n if we're multiplying over and over again. I need, if I plug in 1, I need to get 5. There's a couple different ways you could take care of this. If I plug in 1, I'm going to have 2. So to get 5, I'm going to have to multiply by 5 halves. And that's a good way to do it. More often, you'll probably see it written like this. Instead of 2 to the n, we're going to go 2 to the n minus 1. And that way, when I plug in 1, I get 2 to the 0, which is 1. So then I can just multiply it by 5. And I don't have to worry about 5/2 there. Either one's acceptable. Either one would be correct. 2, -6, 12, -20, 30. First thing I would notice is it alternates back and forth between positive and negative. So we're going to need to take care of that. Let's do that first. A sub n equals -1 to the n, or n minus 1. I want my second term to be negative. So if I plug in 1, I want to get a positive value. Plug in 2 gives me a negative value. And then this one, it's not real clear. We don't need to worry about the negatives anymore. If we try to go geometric, notice this is times 3, and then this is times 2, and this isn't times any integer. So that's probably not going to work. If we do go arithmetic, this is +4. This is +6. This is +8. This is +10. So it's not arithmetic. I'll move this guy down to give me a little more room. One thing you can do, sometimes it'll be quadratic, or it could even be cubic. To tell if it's quadratic, so you do this once. If these numbers here all match up, it is linear. If you do this again, notice these differ by 2. These differ by 2. These differ by 2. If these match up, it's quadratic. If you did it again and those match up, it's cubic, and so on. So this is a quadratic here. It's quadratic. So we know it's squared. So now I would kind of start thinking, again, don't worry about the negatives. We've already taken care of the negatives. Now I'd start thinking, okay, I have 1 squared. I know 1 squared. I need to get to 2. Yeah, there's a couple different ways you could get to 2. We could do times 2. Well, this needs to be 2 squared times, so that gives me 4. 3/2. That doesn't look likely. These aren't matching up. These aren't kind of the same, right? Here, this would be 3 squared. That's 9. So times 12/9, which reduces to 4/3. So it doesn't look like it's going to be something where it's times. If I want 2, I could also do 1 squared plus 1. 1 plus 1. Here I've got 2 squared. 4 plus 2. Here I've got 3 squared plus 3. 4 squared plus 4. And hopefully we're starting to recognize a pattern. 5 squared plus 5. So this is n squared plus n. So some of them a little bit of kind of guess and check, mess with to see what we can find out. If it's not arithmetic, not geometric, I'd kind of check to see, is it quadratic? And you can again do that by doing the difference twice. And if they match up, then it's going to be quadratic. One more type of these. This one, it's got a different pattern on the top than it does on the bottom. You can worry about each one individually. So this one times 3, times 3, times 3, times 3. So the top is 3 to the n. If I plug in 1, I get 3. Plug in 2 gives me 9, so I don't need to worry about like the -1 or anything. On the bottom, I've got 1. This is times 2, times 3, times 4, times 5. So this looks like it's factorial if it's times 2 and then times 3 more and then times 4 more and then times 5 more. For you n factorial, 1 factorial is 1, 2 factorial is 2, 3 times 2 times 1, 4 times 3 times 2 times 1. There we go. You try this set, pause the video, see what you can do on these. Once you think you have them, go go ahead and get her started back up. This first set is quadratic. Notice this is plus 3, plus 5, plus 7, plus 9, plus 11. If we do it again, plus 2, plus 2, plus 2, plus 2. So it is quadratic. This one would be 1 squared plus 4. This one is 2 squared plus 4. 3 squared plus 4. 16 plus 4. 25 plus 4. 36 plus 4. A sub n is n squared plus 4. Second one here is alternating. Negative, positive, negative, positive. First one's negative. Divide by 3, divide by 3, divide by 3. Dividing by 3 is the same as multiplying by 1/3. I'm going to do that n minus 1. That way when I plug in 1 here, I get 1. So I can just do times 81. Again, you can check. If I plug in 1, I get 81. Plug in 2 would be 81 times 1/3, which is divided by 3, and so on. On the bottom, looks like we are dividing by 2 each time. So we can do 1/2 to the n minus 1. Start with 8. This would be a fine answer. If it is multiple choice, you probably won't see it written like this, where we have a fraction on the top and a fraction on the bottom. Usually you'll probably see, I can flip this and move it up. So like 2 to the n minus 1, 3 to the n minus 1. Basically, I'm flipping it, moving it down to the bottom. Multiplying by 1/3 is the same as dividing by 3. And then they probably would combine these two, do 81 over 8 times 2/3 to the n minus 1. Again, this answer's fine. Just know how to match that up if it's multiple choice. Plus 6, plus 6, plus 6, plus 6. A sub n equals 15 plus 6n. The numerator here is plus 1. Would have to start at 4 to get 5 in my first term. Down here we are subtracting 2 each time. Confirm by plugging 1 into the top. 2, 3, 4. If I plug 1 into the bottom, I get -1. Plugging 2 in gives me -3, and so on. And then the last thing we need to talk about for sequences is how to tell if a sequence is going to converge or diverge. So the sequence itself, not the series, so we're not adding it up yet. That'll be the rest of this unit. But the sequence itself converges to L if we take the limit as n approaches infinity of the sequence, and we get L. If the limit does not exist, then the sequence diverges. So like this one here asks us to determine the convergence or divergence of the sequence. If the sequence converges, state what it converges to. So we would evaluate the limit as n approaches infinity. 3 plus 6n squared plus 4n minus 1 over 2n squared minus 1. Degree on the top is 2 and on the bottom is 2. So we divide the leading coefficients, 6 divided by 2. Because I get something, it converges to 6. Oh. If it was like this, where the degree is bigger on the top, this part would not exist. Therefore, it would diverge in that case. And then the last thing, this is for an alternating series. How to check to see if an alternating series converges or not. I'm sorry, an alternating sequence. So what we can do is we can take the absolute value of the sequence. So basically disregard the negative part. If the limit as n approaches infinity without the negative is 0, then the sequence converges to 0. If the limit is anything but 0, so if it diverges or it goes to something other than 0, then the sequence diverges. And the reason for that is, suppose that the limit as n approaches infinity was 2. So when I get way out here, way down the line on the sequence, eventually my numbers would be getting very, very close to 2, and then the next one would be -2, and then the next one would be 2, and then -2. So because it's alternating back and forth between positives and negatives, it diverges. Whereas here, it's getting close to 0, and then getting infinitely close to -0, which is also 0. And then +0, and then -0. So it does get close to 0 if the limit goes to 0. So on one like this, first thing you would do is recognize that this is alternating, because we have the -1 to the n plus 1. So we want to evaluate the limit as n goes to infinity without the absolute value. Use L'Hopital's rule. One over n divided by 2n would be 1 over 2n squared. As n goes to infinity, the degree is bigger on the bottom, so this goes to 0. With an alternating series, or alternating sequence, it only converges if it is going to 0. This one here, we would evaluate the limit as n goes to infinity of this guy here. Degrees are the same. Divide the leading coefficients. 3 divided by 6, which is 1/2. 1/2 is not 0. Because it is alternating and is not going to 0, it diverges. If it looked like this, then it would converge to 1/2. Alternating sequences will only converge if they're going to 0. That's it for the notes on lesson 2 on sequences. I lied. One more example, sorry. The very last one here, if we do have factorials, n minus 3 factorial over n minus 1 factorial, you're going to take the bigger one, which n minus 1 is bigger than n minus 3, because they're both negative. The one closer to 0 is the bigger one. Factorial means start with that and multiply that and then subtract 1. So like if it's 5 factorial, we do 5, and then we do 5 minus 1, and then 4 minus 1, and so on, right? So here I've got n minus 1. N minus 1 minus 1 would be n minus 2. Minus 1 again would be n minus 3. On down, so I'm going to write it as n minus 3 factorial. And I stop there because now these n minus 3 factorials cancel. We are checking the limit as n goes to infinity. Because I have n's left on the bottom and none on the top, this is 0. It converges to 0. All right, for real this time, that is the end of the notes. Reach out if you are having questions.